Chapter 5, Torsion, Indeterminate Example. In this example, like previous problem you review, we have indeterminate torsion example, steel shaft embedded in aluminum tube. External part is a aluminum tube, outer radius of 38, thickness of 8, make it like inner radius 4, so it just make it aluminum like R2 38 millimeters. If you subtract the thickness from that, it just gives you a 30 millimeters for inner radius of aluminum tube. And for other part, it just provided to 5. They are connected to a fixed support, so they are kind of a parallel condition, and a cap at free ends. So there is, we just remove that one, but there should be a cap here which connect both and then torsion applied to that cap. We just take out the gap to show the effect of torsion in the cross-sectional area of our structure here. So there should be a cap to keep them in parallel condition. So a torsional torque of 6325 Newton applied at the cap at the free end. And we want to know what is the share of torsion in solid shaft. As soon as we have part A, we want then what is the maximum shear stress in solid shaft. So as soon as we have torsion share for steel, can have tau is equal to Tc over J. By applying this equation and replace that by portion of steel, we can easily get the tau maximum in steel shaft. So G steel is G for steel is 77 gigapascal, and for aluminum is 27. Let's approach our problem. So with using of equilibrium equation, we can get, we just know the combination of torsion, share of torsion for steel plus torsion of aluminum is the T, total T, which is applied like almost 60 to 5 newtons. Compatibility of displacement, it just says as if it's a parallel condition. If they are rotating with each other, the compatibility says the phi angle of twist of steel is equal to angle of twist of aluminum. And load displacement is just expansion of the second equation, just gives us phi steel is T L over Gj for each material. So this is for a steel part, this is for aluminum. They are equal to each other. You can also cancel out the length because both of them having a equal length of 500 millimeters. So if you calculate J, polar moment of inertia, for the aluminum tube, it just gives you the new value of this much. G of aluminum is 27. The same for steel gives you value of 0.614 times 10 to negative 6 meters. The rigidity modulus of steel is 77 gigapascal. So then if you apply this equation, it just gives a relation which connect T1, T steel or T1 for example to the aluminum. Two material are connected to each other to like with a coefficient of 0.87. So if we do know that the torsion of share of torsion of steel of torsion is equal to almost 90% of share of aluminum torsion, and applying these two equations, we just get this relation, and we do the total summation of them should go by the total amount of torsion. So if we have these two equations, place the T steel, T aluminum based off T steel. So it just gives us T aluminum is T steel times 1 over 0.874, and it just gives us the total value. If you solve this equation, it just gives you a share of torsion of steel is 2951. And at the same time, from this equation, we do steel is controlling. Why is that? Because the share of steel in torsion is 80, almost 8% of T of aluminum. So T steel is smaller. T smaller is controlling part, because if you get the larger number for controlling part, the maximum stress in the first bond exceeded the allowable acceptable stress. So that's why we already know that the steel is controlling, and it just gives us a numeric value of steel of 2951.7 Newton meters. And for part B, if you just replace T steel in function of tau or shear stress, it just gives us a T steel, which is 2951 over C, which is the radius of steel, which is 25 millimeters, over J, which is this numeric value, and it just gives you 120 megapascal. If you remember the previous video, which I can review that as well, this one we just provided to have a tau maximum. It just solved the problem in different way, and it just reached to the same new value for tau allowable for steel. Thank you. We solve more problems. So it just gives us a tau maximum for steel. And compare this answer with the problem statement of previous video to verify if they are need the same numeric value or. Thank you.